learning, molecular imaging, and early cancer detection. So Gaeun.
Hello everyone, thank you all for coming. So today I'm going to be talking about the intersection between machine learning and medical imaging and the implications that has for the future of early cancer detection. So first I'm going to talk about early detection and why it matters in the first place. Why what I'm going to be rambling about for the next 20 minutes is something that the world should actually care about. So first of all, there have been numerous important advancements in our global battle against cancer. We've, for instance, invented the refrigerator, which has decreased occurrences of some cancer. We've also improved techniques of resection surgery, of radiation therapy, of chemotherapy. All of these different things are incredible advancements that are important in ultimately providing a 100% survival rate for cancer. But what I think matters perhaps even more than finding a cure for cancer is being able to detect it at its earliest stages. Because by being able to do so, we're going to start treatment when the treatment is actually going to be effective, rather than when the survival rate is dismally low, like 5% or 10%. And the numbers actually speak for themselves. If you look at this graph above, in the case of breast cancer, if you detected it in the earliest stages, as in stage 1 or 2, you have almost a 91% rate of survival, whereas if you detected it later in stages 3 or 4, there's a dismal 16% rate of survival. And the same goes for colon cancer, skin cancer, ovarian cancer. All of these are cancerous, or all of these are cancers that we want to cure. But if we detect them in the later stages, there is less than 20% chance of survival in most patients. And this is why early detection matters so much. If we're able to make early detection accessible for everyone, to make sure that everyone gets it just like a regular checkup, we could increase the cancer survival rate potentially by 5 times more even, and that is a huge advancement in our battle against cancer. So having said that, I want to look at medical imaging, and why medical imaging, I think, is in particular an art that is important for cancer detection and for advancing this field in general. You see 2 images here. The first one is a full-body PET scan. The second one is a liver ultrasound. If you look at the left image, this is actually quite unfortunate because you see all these red things lighting up in the person's body, and all those red things are actually tumors. So besides the brain, which is red because it's filled with blood and the contrast agent rushes to the brain, all of these other red spots are tumors. And while this image itself is unfortunate, it's incredibly beneficial in the medical industry because we can pinpoint exactly where the tumors are located in the body. So when we're doing things like radiation therapy, we can specifically target those tumor points rather than having to cut open the body, or in the worst case situation, doing surgery just for the sake of exploration, which is what we don't want. It is bad for patients' health. And the second image you see on the right is a liver ultrasound. Ultrasounds are different from PET scans, but they serve a similar role. You see the 2 conspicuous red arrows pointing at a huge black hole inside the ultrasound. That is the tumor that we want to identify, and there's a white ring surrounding it to indicate that it is indeed a tumor. And so the benefit of both of these images is ultimately that through PET scans or CT scans, MRIs, ultrasounds, etc., we're able to empower physicians and researchers to see through the body, to see through the external appearances of the patient. So even if there are no external manifestations of the symptoms, we're able to see through the body and pinpoint exactly where the cancer is located and how we might go about treating that cancer. And these days they created molecularly targeted contrast agents where we inject like antibodies or ligands into the patient's body before doing any of these scans, so that the contrast between the tumor and the organ surrounding it increases and we can see it even more accurately. And so with all of these advancements, these have incredible implications in cancer detection and treatment monitoring. So in the case of cancer detection, because we're able to so accurately identify the location and the size of the tumors, we're able to identify them at the earliest stages, and therefore we're able to take steps to prevent them from further metastasizing or developing into larger tumors. And the case of treatment monitoring is also useful because through ultrasounds, rather than cutting open the patient's body through invasive procedures like biopsies, we're actually able to quantify exactly the size of the tumor and whether the treatment that we're currently doing is working or not. So that's useful for physicians in many aspects. And one thing that our lab at the Stanford Canary Center is focusing on is 4D ultrasounds, or in more pretentious terms, volumetric contrast enhanced ultrasounds. And essentially, we're adding a 4th dimension to the 3 dimensions that are already present. You have the frontal axis, the sagittal axis, and the longitudinal axis. We're adding the time dimension so that we can map the changes in these 3 axes onto time. And the benefit of that, and the reason why we're so interested in using that, is that 4D volumetric ultrasounds lead to greater sensitivity. So whereas a 3D ultrasound will be selecting a random point in time and showing the doctors a slice of the tumor during that time, 4D ultrasounds are actually able to show the progress of the tumor throughout a minute or even a few minutes perhaps. And you can see the changes in this graph published in a paper in 2012. This is what happens when you do 4D ultrasound scans on the liver. They scanned the liver before treatment and then 2 weeks after treatment, whereas in a 3D ultrasound, you wouldn't see much of a big change. In a 4D ultrasound, you clearly see that, according to figure B, the red part in blood perfusion significantly increased after treatment, meaning that the treatment is actually working. And these are things that we would have never been able to notice if we were to just rely on 3D ultrasounds. And that's why I think 4D ultrasounds are so useful and present incredible potential in the field of medical imaging and early detection of cancer. But there's one big problem that's preventing us from practically and clinically implementing any of this technology, and it's the problem of motion correction. So the challenge, especially when we're looking at stomach cancers, like liver cancer, is that breathing motion distorts the images. So unless we sedate the patient completely, which is something that's terrible for the patient is going to breathe. And that sort of breathing is going to cover up the tumor with various other organs, especially the ribs. And that's going to distort the images to the extent where the tumor itself escapes the frame and we're unable to identify the size of it, nor are we able to track if the treatment is actually working. So this is a huge problem. One of the main reasons why this occurs is due to the slow frame rate of 4D ultrasounds. That because we're importing a large amount of data, including the time axis, it takes more time for each slice to process itself, and there is therefore a large frame-to-frame disparity. And there are several challenges here in motion correction. I'm going to play this quick video to show you what exactly we're looking at, what the problem is. So what I want everyone to focus on is the black spot right in the middle, like I just showed you in the previous slide, and see whether that black spot stays right there in the center of the ultrasound. And spoiler alert, it's not going to stay there. So this is what happens. It keeps moving in and out of the frame, where you see gray spots, and then you see black spot again, and you see more gray spots. And this makes it incredibly hard for physicians to exactly pinpoint where the tumor is and how large it is in general. That's the problem that our lab is trying to tackle. So if you look at it on a frame-by-frame basis, you'll see that in this first frame, time point 35, there is no tumor and everything is gray. Whereas in time point 36, you see this black hole in the middle, so in fact we do see the tumor. So there's this incredible volatility that we cannot control without any sort of image processing algorithms, and we want to apply the image processing algorithms. Our lab decided to use a combination of image processing, image segmentation, and machine learning algorithms to solve this problem of motion correction and to make sure that the tumor stays right where we want it to stay, in the center of the ultrasound where it's most visible to the radiologist. And guess where we find our solutions? We find it in open source software. And no, I didn't just include the slide because it's an open source tech conference. I want to mainly introduce 3 types of tools that our lab frequently uses. The first one is MeVisLab. MeVisLab stands for Medical Vision Lab. And some of the major benefits of this tool is that, number one, you're able to do manual ROI selection. And by ROI, I mean region of interest. So if we're interested in specifically looking at the tumor, we're able to manually color it in. It's actually quite fun job to paint the tumor in, and then through the process of image registration, we're able to make sure that the tumor stays right at the center of the image. And obviously we want to automate the process as much as possible, but when doing the initial data experimentation, such manual selection can be useful as well. I think one of the biggest advantages of MeVisLab is this drag and drop interface where you have different modules. So you have a reader module, a viewer module, a selection module, and then you can just connect those modules seamlessly so that when you input a 4D ultrasound image, it's going to run you through all of those modules and give you a final output without having to write thousands of lines of code and scripting and running all of that, investing many hours in that. They also have developer support, since it's an open source software technology, where you can create your own modules as well, where if you create automated segmentation algorithms for your own ROIs, you can simply drag and drop that as well after you write the code. So it's very easily integrated into the goals of your project, so it's a very flexible tool. And the second one I want to introduce is ITK Snap. ITK Snap also allows for manual ROI selection, but allows for a greater diversity of types of selection. So there's lasso selection, where you drag like a spherical shape across the ROI, and there's shape selection, where you designate a polygon that matches the shape of the tumor the most. But most importantly, you're allowed to develop automated segmentation algorithms. So fun fact about ITK-SNAP is that it was initially developed for brain MRI segmentation, where you have different parts of the brain like the cerebral cortex and the hippocampus, and you want to specifically look at one part of the brain. They initially had automated algorithms to identify those, but now you can apply to different types of medical imaging samples as well. So even when you're looking at liver ultrasound, which is what our lab focuses on, you can create automated segmentation algorithms and view the results directly in ITK-SNAP. So that's one of the greatest advantages of this piece of software. The last thing that we frequently use is FSLView. FSLView is pretty similar to MeVisLab in terms of its functionality and purpose, except the drag and drop function. But the major advantage of this one is that there's easy integration with the FSL toolkit. And the FSL toolkit is a whole series of modules and functions that automates processes for you. So if you want to merge 3D images into a single 4D sequence, you can use FSL merge as a function. And all of these can be integrated into a bash script, and then if you run that through the command line, ta-da, you have your final output. And you can view that in FSLView as well. So there is this seamless integration with the very own toolkit that their lab developed. And so through these solutions, and here's just one quick example of what MeVisLab looks like. Again, you see the modules that were dragged and dropped, and the final output is right there, without us having to go through the whole process of exporting it to the ultrasound machine and then looking at it once again. You can do it all at the convenience of your computer screen. So this is what MeVisLab looks like, and the other pieces of software look pretty similar as well. And through these pieces of software, what the goal of using all of these is that we want to process the images so that, for instance, the contrast is increased. So when there is a large amount of white space and then there's a tumor that is black, we might want to increase the contrast so that the tumor is even more black and is even more prominent in the image. And that's what these open source software technologies allows us to do. But besides that, once we've gone through the initial image processing step, we now want to do something more advanced, where we want to isolate the tumor from the rest of the organ. So we want to get rid of the ribs, we want to get rid of the lungs, which sounds not out of context, but in the context of medical imaging, we want to get rid of them so that we can only focus on the tumor, because that's our primary goal here. And we do that through several machine learning algorithms. In particular, we take advantage of the time dimension in 4D ultrasounds. So first, you perform a maximum intensity projection on all the image slices, where you take the maximum intensity of each pixel inside the image, you project that across the time frame. After that, we use a bag of features algorithm with the pixel intensity and texture as features to classify whether a given pixel in the image is actually black or white, and therefore corresponds to a tumor or a rib or another organ. So we're able to accurately classify that, and we're able to identify the specific region that we think is a tumor. And what is the result of all that? That's what you get. You see the little hairlines around the tumor, and that's the automated identification of ROI. This is a pretty successful example of what our machine learning algorithm can do. So ultimately, we developed this whole pipeline at our lab. So first, you have the original 4D ultrasound sequence. After that, you segment them into 3D frames within a single window using MeVisLab as you saw previously. So you slice the 4D ultrasound sequence into multiple frames, or multiple windows, and inside that window you have a lot of different 3D frames. So we take those 3D frames, and we run them through the machine learning algorithm to isolate the tumor. After which we put them through a fine registration and image processing to increase the contrast for the tumor and to identify it even more correctly. Now the final result of that is again a cube-shaped, I guess, a visualization of that would be a cube, where you have a combination of all these 3D frames and you have a smaller 4D ultrasound sequence. So this is the registered window average, and this is called the window to master average approach, where you register the average to a single window and then you register all those windows to a master average. Whoops. Let me fast forward that. So you have all these algorithms, you have the window average, and then finally you register all of the individual windows to the master average, and that's the final registration step. And the pipeline that we developed actually works, and just to show you that it does work, the top is an example of uncorrected, and you see that the black hole there moves around and disappears in the frame quite often. In the bottom image, you see that the frame and the hole stays right in the center, and that is a consequence of all the machine learning and image processing algorithms we put it through. And in the second column in the bottom right here, if you look carefully, you'll see that the image continuously warps itself. So it warps itself across time using all of the algorithms that we implemented, and through that process, it makes sure that the tumor, the big black hole, stays right in the center. Whereas in the first row, which is the uncorrected version, you don't see any of that warping happening. And so this is going to allow us to accurately quantify the size of the tumor, and as I said, is going to be useful in terms of early cancer detection and in terms of monitoring treatment progress in patients as well. So this is specifically for liver ultrasounds, but we see numerous applications in different types of cancer as well. So how did I end up doing all of this? How do you contribute to medical imaging? I have a few suggestions, and this is actually a very fun project that you could take upon in your free time if you have any. And I forgot to mention this, but I'm a high schooler, and I was originally, I'm supposed to be in the midst of college apps right now, but I used this intellectual conference as an excuse to go on a nice vacation to Singapore. First off, I tried to discover and contribute to open source projects. So I found this thing called Luna 2016. The name sounded interesting, and it was ultimately about lung nodule analysis, where you took multiple CT scans of the lungs, and then you looked at whether there were cancerous regions in it, and it was essentially an online challenge. There was also the Cancer Imaging Archive, where you can have access to thousands and thousands of CT scans from cancer patients, all for free in a public database. You can literally just click a few buttons and download DICOM files as you go. There's also Kaggle, well known to a lot of data scientists. They have numerous data science competitions that are related to medical imaging. And recently, I think it ended a few days ago, but they had the Harvard Tumor Hunt, where essentially you took, again, samples of lung cancer CT scans, and you tried to classify whether they were cancerous or not. There's also the BRATS challenge, which sounds weird to most people, and it's about brain tumor segmentation challenge. And so, although none of these are related to liver ultrasounds, which is what we deal with in our lab, all of them are related to medical imaging. And the implications are huge, despite the fact that you can do it inside your own room, on your computer. And so through all of these public open source databases, you can just download the data and you can play with them on your own. And there are multiple tutorials online on how to do lung segmentation through UNet algorithms, for instance. And so through these open source projects, you can actually contribute to real life algorithms that are implemented in the clinical setting. Especially given that the open source community in medical imaging is so active these days, if you make a pull request to include an algorithm in a certain project, then it will actually become included. And you will be able to improve the accuracy of cancer diagnostic algorithms, and you will be able to make a difference in the medical imaging field. And so I took it a little further than that. I went to cancerbase.org and looked at a map of all the people who contributed to cancerbase.org, got really interested in this, and I emailed a bunch of professors at Stanford and sought out lab opportunities. But even besides that, just simply raising awareness and participating in these data science competitions is actually a really significant contribution to the medical field and to the field of early cancer detection. To specifically talk about cancerbase.org for a little while, cancerbase.org is not actually a diagnostic challenge. It is more of a database of stories from cancer patients rather than CT scans or quantitative analysis. Essentially, multiple cancer patients from around the world share their stories of their treatments, what sort of treatment they received, did it work or not, what was their experience like undergoing that treatment. And so it's a website where you can share all these stories, share data as well, and researchers take advantage of that data to further their research in cancer imaging and in medical imaging in general. And so you're able to raise awareness in these methods. Even if you don't directly contribute to the algorithms themselves, you're able to just visit these websites and read through the stories and look at the incredible prowess that medical imaging has provided to this field. And so these are the numerous ways that you can contribute to medical imaging. Given the trend of open source projects these days, it's going to be easy to contribute if you just muster up the motivation to do so. And I encourage everyone to try and go on these websites and just play around with the data sets. And that's essentially it. I think medical imaging is a field that's incredibly important for early cancer detection. I hope this was an informative talk, and I'm open to questions if you have any.
Any questions? I've got one.
Okay.
It's incredibly inspiring work, and clearly concise, well presented, with visuals that make sense to me straight away. I can only wish some of the other FOSSASIA presentations were like that. I'm hoping mine will be a little bit like that tomorrow.
So first of all, I think that has a lot to do with the whole reason why I got involved with this field of medical imaging in the first place. I myself explored this field initially through open source projects, and so I really wanted to advance the open source mission and to continue on the reason why I started getting interested in this field in the first place. I also think that it's much more useful to open source these things, especially since machine learning relies on the abundance of data. If you don't have data, if no one contributes data, if you just keep it to yourselves and experiment on the 40 patients you have in your own hospital, that's not going to lead to good results. So both from a utility perspective and from personal motivation, I was more motivated by open source rather than like proprietary software.
It kind of makes sense that for something humanitarian to be shared across and rather than be siloed in something that's corporate and protected. I mean, if this is cancer that everybody faces and it's beneficial to humanity,
Right.
then why not embrace the open source? So it's unbelievably admirable. Has anybody else got questions? We've got one right there.
So more of a comment. Always nice that there's a lot of open source software available, but when it comes to data, it's going to be a big problem now because a lot of these patient data are still being seen as sensitive, and there are of course legal restrictions. So this is going to be a huge challenge moving forward.
Right, so there are a lot of open source databases besides just the code for diagnostics and segmentation. Like the Cancer Imaging Archive is an archive and database of thousands of cancer CT scans for brain cancer like glioblastoma, liver cancer, lung cancer, breast cancer, etc. So there is a huge abundance of data, and like you said, the main challenge is protecting things like personal identity and privacy. But I think universities are doing a great job sort of de-identifying data before they release it. Even I don't know who the experimental subjects at our lab is. I don't know what the code of C1BT13 of the datasets stand for. So there is that level of confidentiality and privacy, but I think the academia part of it does a great job maintaining that. And so although that is a challenge, we're continuously overcoming. So I've been interested in medical imaging since freshman year, which was 2014. And I actually got involved in the research side of things when I joined the lab, which is approximately a year ago, or like 7 months ago.
So you said you make a pull request that gets used by the researchers and stuff. Do you know how much getting used by researchers is one thing, but getting used in every single hospital is quite a lot more? Do you know how much of it moves up all the way, or how long it takes?
Yeah, so unfortunately there is a bit of hiatus between the research step and the actual clinical implementation step. But one of the reasons why we really try to focus on the practical side of things, like motion correction for 4D ultrasounds, isn't a big concern in the research setting, but is a big concern in the clinical setting. So we try to specifically address those concerns that will actually arise once we start experimenting on patients. But in general, when you have these open source projects and you try to apply them to the clinical setting, especially because a lot of these challenges, like online challenges, are hosted by universities like the Harvard Tumor Hunt, it goes directly to the researchers. This gets experimented at the Massachusetts General Hospital or the Harvard Medical School, for instance. And through that process, it does take years of testing because of safety concerns, obviously, like positive, negative falses would be terrible in the case of cancer diagnostics. But because they mostly go through these accredited institutions, the process is made a bit easier than just people getting together and doing their own open source